Well, good morning, everybody, and welcome to the first of today's webinar sessions that we're running here from Smart Vision Europe. We run these webinars on a fairly regular basis, once a month or so, and we usually do about 3 in a day. And the first one we're going to be looking at today is the topic of decision trees. And decision trees are a very popular multivariate technique, a very visual technique that allows us to look at the relationship between several variables, several fields, and a key target field, if you like. So if you haven't joined in these sessions before, just be aware that we do record them. So you'll be able to listen to this session again. We send the link out to you. We also have recordings of pretty much all of our previous webinars, and there's a lot of different topics there. There is some slideware here, so we'll email out a link to you afterwards so that you can download a PDF of it. And if you think it's particularly relevant for colleagues who aren't able to join this morning, then we may be able to arrange a rerun of it. Otherwise, you can share the recording with them. With regard to asking questions, well, all the lines are muted, so we ask you to use the chat panel, and my colleague Rachel Clinton will be monitoring that as we're going along and answering questions. But as I always say, I tend not to look at the chat panel as I'm going along because we've got a lot to fit in. But we do follow up with you afterwards offline. So you can either ask a question in the chat panel or just drop us an email, and we're very happy to answer offline in detail, or even pick up the phone and speak to you if it's easier. So if you don't know who Smart Vision Europe are, we are a gold accredited partner to IBM, and also a company called Predictive Solutions and Data Robot. And we specialize in advanced analytics, big data technologies, AI type technologies, machine learning, etc. We also work with open source technologies such as R and Python and Spark. And we're a relatively small organization made up of a veteran team of people with 15 to 30 years experience working in statistics and advanced analytics and AI software industry. And as a result, that means we've got a lot of pretty deep experience of applying these procedures, these applications, these techniques across many different sectors in the not-for-profit and for-profit world, whether it be retail, gaming, utilities, local government, healthcare, housing, charities, media, telcos, finance, manufacturing, etc. And certainly in all of those sectors, there is a role for the topic that we're going to be talking about this morning, which is decision trees. Now, before we get into decision trees, let's just put it within context. We tend to use the term predictive analytics, which is something of an old-fashioned term here, because it's been subsumed these days by AI. AI is such a generic term these days; it means practically anything. Predictive analytics is a bit narrower than that, and it's really a bunch of techniques that encompass statistical techniques and machine learning and predictive modeling and data mining that really analyze current and historical facts to make predictions about future other unknown events. That's Wikipedia's definition of it. We tend to break it down into a couple of bullet points to make it easier for people so they can understand. This is different from BI or MI reporting. We're not so much interested in describing data and reporting it and monitoring. We're really interested in going somewhat deeper and making forward-looking statements, trying to categorize things. At that point, it starts to sort of bleed into AI. And as a result of that, it's not always about prediction per se, because it could include things like cluster analysis or association analysis or recommendation engines or text mining or analysis of geographical data, etc. But the thing that all of these different techniques within the predictive analytics realm have in common is that they create new data. They create new data that didn't exist before. And that new data can take the form of segments or clusters or probabilities or classifications or categories or sentiment values or propensity scores or risk indices or likelihood outcomes. And that new data can then be turned into key operational or operational data or incorporated operational data so that people can can take actions based upon these predictions or classifications or likelihood values. But they can also be incorporated back into insight systems such as reporting tools like business intelligence or management information systems. So in this example here, we will show you how we can use decision trees, for example, to create new data and to create predictions off the back of that. But we should bear in mind that decision trees as a kind of approach in itself is very powerful, even if we're using it purely for insight purposes. We're not necessarily, even if we're not necessarily interested in operational predictive outcomes, if you like. So there are different types of predictive analytics. I've alluded to some of them so far. Classification and propensity modeling usually means modeling where you've got some sort of category outcome. You know, who's most likely to be satisfied, who's most likely to respond to an offer, who's most likely to upgrade a contract, who's most likely to recommend, which machine is most likely to have a defect in it or need inspection, which patients are most likely to be readmitted to hospital, you know, which healthcare outcomes are more likely than others with survival, etc. So some sort of key category outcome, a yes/no outcome of some sort, or a grouped outcome, low, medium, high, for example. And that's very much the realm that decision trees works within. Other types of analyses include things like clustering, how you divide customers, tenants, patients, citizens into meaningful and usable groups, as described by many factors in the data. Association and sequence, what normal combinations of product purchases or events tend to co-occur. When A happens, B tends to happen, or when A and B happen, C tends to happen, that type of thing. And time series, which is forecasting, where we want to extrapolate, for example, things like demand or revenue or visits or repairs or something like that into the next hour, week, month, quarter, year, etc. These are all types of predictive analytics. We're really focused on the first one here, classification propensity. That's where decision trees fits. And the reason it fits in there is because decision trees can be used to build profiles of customers, employee, clients, tenants, patients, taxpayers, donors, etc., who are most likely to do something or most likely to respond in a particular way. And in doing so, it actually finds key groupings within the data, and these appear as nodes within the trees. We'll talk about that in more detail later on. But it also allows us to effectively generate a predictive model. We could potentially use a decision tree as a predictive model, apply it to new data, and have it produce predictions for us. And that's because decision trees can be expressed as a series of hierarchical rules, which means it can be converted into languages like SQL for database scoring, but can also be expressed in SPSS syntax languages. And because they're effectively rules, you can use those rules to score new data and get it to create, for example, propensity values for you, saying who's most likely to fall into a certain group, whether that be recommendation or whether that be response in some way, or likelihood to reoffend if it's a recidivism application, or likelihood to be readmitted to hospital if it's a healthcare application. Now, decision trees are really popular in this area because compared to other techniques that try to do the similar things, statistical techniques like, for example, logistic regression, these are very visual. So they actually paint a picture of how the variation in the data is split. And they're relatively easy to understand as a result of that, because they're just a series of rules. So you don't have a whole bunch of different coefficients that you're trying to interpret, beta values, B values, you know, standard errors, significance values, that type of stuff that you're trying to interpret, which is, you know, very common with things like regressive techniques. And it's also because it actually gives you some output, which is, you know, often something that you don't get from machine learning techniques like gradient boosting or neural networks. You can't really, they tend to be much more black box, so they don't necessarily deliver a lot of insight. So decision trees are really quite popular because of its it falls somewhere between the classical statistical world and this kind of harder, more obscure, obtuse machine learning world. So if we want to understand decision trees, we usually start with this example. This is a very well-known example. You can actually get this data set off the internet. If you just type in Titanic data set into Google or something like that, you'll probably find more than one version of it out there. But it's a data set, has 2,201 cases in it, each case, of course, representing a passenger on the Titanic. And of course, we know that tragically 68% of people died on the Titanic. So 1,490 people actually did not survive the sinking of the Titanic. 32% did. And if you ask a room full of 30 people or so, what do you think of the factors are that drove survival on the Titanic? Well, we're all familiar with the story. People have seen the movies, etc. So they pretty much guess the three factors. They'll guess the three primary factors, which are going to be gender, age, and their class of travel, as we might expect. Now, when we ask people, well, what do you think is the most important factor in survival on the Titanic? It turns out that people tend to disagree there, or they're wildly guessing. It's not obvious. So one of the things that we use classical statistics for, of course, is to try and identify what are the most important factors driving an outcome. And if we're doing on a sort of case-by-case basis or factor-by-factor basis, then in this case, we might be using something as simple as a cross-tabulation table, and requesting in SPSS, for example, that it also displays chi-square values for us. So if we look at the chi-square values for survival on the Titanic by gender, by sex, we can see it's 73% of females survived. Bearing in mind, of course, there's only 470 females on the Titanic, compared to, which is something that isn't always represented in the movies, etc. The overwhelming majority were male, 1,731. And of those 1,731 male passengers, only 21% survived. And if we were running a statistical test to find out whether or not these two variables, survival and gender, were independent of one another, in other words, if we were testing the null hypothesis that this difference that we're observing is in fact weak enough that we would see it on a regular basis, if you like, it's not really a significant effect, and we would run a chi-square test. And the chi-square test returns a chi-square value to us, and that chi-square value combined with degrees of freedom, which refers to the number of cells in the crosstab and adjustment for the number of cells, gives us a significance value. Significance value here looks like it's 0. It's 0.000, but in reality, it's just, it's probably about 34 decimal places. It's a very, very small number. So that significance value, that probability value there, based on the chi-square statistic, tells us in many ways it's a kind of measure of the effect of, I hate to use the term how significant the outcome is, but it's kind of a measure of how significant it is. The smaller the probability, if you like, then the larger the chi-square value associated with it. So we would conclude that, of course, that the notion that survival and gender were unrelated isn't really substantiated by the evidence, and we would reject the null hypothesis that gender didn't affect survival. We then compared that to age. What we find is that for adults, 31% survived, and for children, 52% survived. Now, that's not as big a discrepancy as 73% female and 21% male. And as a result of that, the chi-square value is much smaller. The significance value looks identical, but that's because we can't see all the decimal places in it. But we would conclude from that it's probably not as big an effect. And we can see that, for example, only 109 children on the Titanic compared to 470 females. So they're an even smaller minority. And then we have we have the class of travel. First class, 62% survived, 41% survived. Second class, 25% survived. Third class, and 24% survived crew. And that also gives us a significance value. Now, I think that if we were to look at the actual probabilities, it would come out as something like, gender followed by class followed by whether or not you're an adult or a child. And you might think, well, that's it. Now we've established the rules there. We've seen all that. But what decision trees are really good at? Decision trees are really good at finding exceptions to rules. They find interactions between the variables. So, if you said, look, let's assume that class is the next most important factor after gender. Is that true for males and females, for example? We might say, is the difference in survival between adult and children the same for males and females, or is it different? And these are things that decision trees help us to establish and help us to find the hot spots, if you like, in the data where survival is elevated and where it's very much suppressed. And even with three simple factors like this, we've only got three variables here. Two of the variables only have two outcomes. One variable has four outcomes. Even then, we can create quite a nuanced and interesting decision tree just with these four variables. And we'll see an example of that in a moment. So when we create this decision tree, it's important to understand how you're going to interpret it. This is what it's going to look like. It's going to show you right at the top what's called the dependent or the target field. That's your key field. Now, remember that in this example here, the key field is survival. It's showing us, of course, that there are 2,201 people, that 32% survived and 67% did not. So everything that happens after that point is that these 2,201 cases are then split into groups until eventually they come into groups that are so small that the decision tree can't go any further, or where it can no longer find any statistical differences. Because what the decision tree does at this stage is it tests each field in turn, sex or gender, age, and class of travel, against this target field. And the variable with the smallest p value, the smallest probability value, is the one which is seen as the greatest discriminator, if you like, between survival and non-survival. And therefore, that is entered into the tree first. And then that splits the data, and then the data splits again within that. So when we were interpreting the tree, we're seeing this dependent target field. Bear in mind that although the boxes look like they're similar sizes, in reality, you've got to keep your eye on the total value here, which is 470 females, 1,731 males. We can see here that it also shades the modal group, the group of the larger number of cases. So did not survive is shaded gray here, indicating that 78% of the males did not survive, whereas for females, 73% did survive, so that's shaded. And it also gives these nodes, as it's called, these split groups, if you like, these different categories, what are called node numbers. So we'll be able to extract the node numbers at each point and say, well, which group did that belong to? On a case-by-case basis, you'll be able to say, well, that case ended up in a node, because they all end up in a final point, a bit like a train network. They end up at a final station. And this is what the full shade decision tree for this particular tree looks like. And you can see we have these endpoints called terminal nodes. This is the bit where somebody gets to the end and they can't go any further. So if we were looking at the 2,201 cases and we look at the male branch, what we find is that for male survival, 78% survived. If they're adult males, then actually, 78.8% did not survive. If they're adult males, 79.7% did not survive. So it actually goes up slightly higher. If they're adult, if they're child males, then 54.7% did not survive. And then it splits it into class. And what's interesting here is that we get an interesting exception to the rule. Previously, we saw survival rate decreasing between first, second, and third class. But here, if we're looking at male adult passengers, in fact, survival for first-class passengers was 32%. For second-class passengers was 8%. For third-class passengers was 16%. And for crew was 22%. So actually, the group with the lowest survival rate is the one in terminal node number 9, which are second-class passengers who are adult males. And there are 168 of them, and only 8% survived, which is interesting because that's not kind of the general effect that people know about. This is an exception to the rule. In the same sense, we look at the female branch over here, we can see that we've got first class, second and crew have been combined together, and third class. Okay, so 97% of females in first class survived. Of second class female passengers and female crew passengers, 87% survived. That's 113. And for those traveling third class, the majority did not survive. 54% did not survive. 45.9% survived. So again, it's saying, well, age is not important. if you're a female passenger, it's not a statistically significant effect. It does not get entered. Secondly, that second class and crew, the difference in survival rates for them was so small that it actually was able to combine those groups together without changing the overall significance of the test here, which splits the data effectively. And this particular algorithm that's running here, it's only one of the three algorithms that decision trees have in SPSS. It's called CHAID. It's one of the most famous ones. And it stands for chi-square automatic interaction detector. In each of these final nodes here, they're effectively generating percentage survival chances. These are the same as probability. So the probability here of survival for males in second class who are adults is 0.83. Here it appears as 8.3%. That as a probability, that's 0.083. 8.83 would be 83%. 0.083. Here it would be 0.162. Here it would be 0.223. So it's going to turn these final groups here into probability scores for us. Something that else is important here, we didn't have any continuous variables in here. We didn't have a scale field, so we didn't have something like, the amount of money that they spent on their ticket. In fact, in at least one of the data sets you can download, it will show you all of that information about the Titanic passengers, how much they paid for their ticket and what cabin they were staying in, etc., etc. But if you did have a continuous variable and you added that into your decision tree, it will happily accept it. And it's really powerful and useful because what it will do is it will take a continuous variable and by default, it will split it into tenths. So it puts it into deciles. It will try to get 10% of the cases in each of the deciles. So it's splitting them into tenths. So effectively has 10 groups and then it groups them together, those groups which are contiguous to one another, but which are not statistically different. And that's really powerful because, for example, here we can find the threshold points at which buying a financial service changes based on the amount of savings or investment that particular customer has. And we can say that, well, if it's less than or equal to 4,395, 28% of them have the savings investment product. If it's between 4,395 to 6,150, that jumps by 20% to 48%. And if it jumps from there from 6,100 to 8,000, it jumps again by just under 20%, 63% here. And if you get above 8,000, it jumps again to 78%. So it's actually showing us the thresholds where this this outcome here is affected, and it's showing it in quite a pleasing way. It's each threshold that's going up, this value is going up. It's not always the case. Sometimes it finds these non-linear groups, these groups within it. But even on that basis, it's very powerful. This is sometimes known as optimal binning because it's finding the optimal bin groups or the banded groups, if you like, within a continuous variable. And that can, as I say, just within itself can be very powerful and interesting. Okay, so that's our lead up to it. Let's spend the rest of the session now just looking at how we can run decision trees within the SPSS. I'm going to open up a data set here. I'm going to open up a little data set called Insurance Train. Insurance Train means it's a training data set. And we've got a key variable. Our key variable is, do they have our bank's home insurance product, yes or no? Okay, so 45% of the people in this grouping here, there's only 300 cases, so it's a much smaller data set, bear in mind, than the one that we saw earlier in Titanic. It's only 300 cases here, very small data set. That's our key outcome. We are interested in this key outcome. Well, given that our baseline is 45% those who bought the insurance product, we're interested in which groups do we find within the data set, within the data, where that value is significantly higher or significantly lower. And if we look at the different fields we have a mix of continuous fields. We have this field here called children, which just goes from 0 to 3. I think we can assume that 3 means 3 or more. It seems odd that, in 300 customers here that, the maximum number of kids they got is only 3. We have income in dollars here, so that's running from 5,000 to 63,000. We don't know how old this data set is. We can assume it's fairly old. And age here, we have continuous age. We have that's running from 18 to 67. So not very many people aged over 67. Again, it's obviously a particular cut of the data. And gender here, we have nearly even split, 48%, 51% split between males and females. And we've got other variables like their marital status, whether or not they own a car, whether or not they have a savings account with that bank, whether or not they have a current account with that bank, whether or not they have a mortgage with that bank, and whether or not, of course, whether or not they have home insurance, which is our key factor. Now, any one of these could have been our key factor. We might have been trying to target people for a savings account or target people to get a current account or a mortgage, something like that. But it turns out that it's home insurance that they're interested in. And that's key because with decision trees, there's always one key thing that you're interested in. And it could be an operational outcome like this. It could be whether or not they've purchased a product. But bear in mind, it could also be something like satisfaction. It could be likelihood to recommend. It could be your net promoter score. It could be some sort of measure of trust. It could be whether or not that patient has been readmitted to hospital. It could be whether or not that machine has needed maintenance. It could be anything. But it's some sort of key outcome, usually a KPI or something that people that measure. And we want to run decision trees. We're going to find that in the Analyze menu here, it is a module within the SPSS. So if you don't have, if you're seeing under Classify here and you're not seeing Tree, it means you haven't got the decision tree module. Okay, so it's an additional module that you get within SPSS. I think it's included in the Professional and certainly within the Premium pack, but you can also get it individually. So you can add it to your SPSS in a base installation individually. If you click Tree at this point, we're going to pick, it says dependent variable here. Don't get thrown by that. That just means target field. And our target field here happens to be home insurance. You can see here it says categories. I'll come to that more, and I'll just return to that later on. But I want to build a really basic tree at the moment. I'm just going with the default options. I'm choosing everything but customer ID. Of course, we don't want to be choosing customer ID. And you can see here that there's more than one decision tree method. We actually have CHAID, exhaustive CHAID, something called CRT and Quest. And there's something else called an influence variable here. If I run with this and just show you the default settings, we'll see the output from that. So the default settings here, it produces a really, really simple tree for us, okay? And we can talk about why that is in a moment, but let's just have a look at it. And it's saying to us, I've found two factors here, which really help us understand what discriminates between people who buy home insurance and those who don't. 45% people did buy the home insurance product within the bank. And what it's saying is that number of kids that you have is actually the biggest predictor of whether or not you have home insurance. That could be some sort of measure of disposable income, I guess, or something like that. Don't know. But it's saying here, it's labeled oddly because it's saying number of children here is 0, 1, 0, less than or equal to 0, 0, 1, and greater than 1. I do find that the labeling of ranges is a bit complicated. It's a bit obscure and a bit hard to get your head around. That just means 0 if you've got no kids, and that just means 1 kid, and that means more than 1 kid. You should bear in mind, if you double click on the tree output, you can open it into its own editor, and we'll be doing this a lot. And what I find is if I do that, if I go to options and switch on ranges as text, sometimes that's a little bit more helpful. So it's saying 0 or less, higher than 0 through 1 just means 1, and higher than 1. Sometimes people find that. So that's options, ranges as text. Well, it says if you've got 0 or less kids and there's only 35, say 36% of people buy the product. If it's actually 1 kid, it's 85% buy the product, and then it drops again to 32%. So it's non-linear. It's not saying the more kids you have, the more likely you are to buy the product. So it's kind of interesting. There's this sort of magic sweet spot where if they've got 1 kid, they're more likely to buy the product. But if they have got more than 1 kid, then there's an exception to the rule. It says, well, if you're age 41 or less, then only 12% have this product. And if it's more than 41, then it's 54% have this product. So it's finding this exception to the rule in the 110 cases here. And that's all we have to do at that point. We can see the chi-square value here is P000 at each point. So these are statistically significant splits. The reason why the other fields haven't been chosen is because either they weren't statistically significant or they weren't the most statistically significant at that split, or it could be that it's creating group sizes which are too small for the tree. We also get this risk table here and this classification table. This is actually telling us, it's saying if I was just using these 4 terminal nodes here, node 1, 2, 4, and 5 here, to predict the outcomes, to predict whether or not somebody had a decision tree, it's basic. Whether or not somebody had a home insurance product, it's actually saying that you'd be accurate in the no group 80% of the time and accurate in the yes group 60% of the time. So it's actually 71% accurate overall. Whereas if you're choosing it randomly, the best you could hope for is 55% accurate. That would just be assuming everybody was a no. That'd be the best you could do. The risk value here is really just this value estimate here isn't really relevant here, but it's just basically the delta between the overall percentage and the error in that. So it's more or less that it's close to about 30%. That's basically saying 28.7%. It means 28.7% error, basically. That's what it means. So it's not terribly interesting. Obviously, the larger that number is, then the larger that value is, the closer it is to 1, then the more error there is in the tree. Let's rerun the tree. If we want to rerun the tree, we go to Analyze, down to Classify, and down to Tree again. And we'll investigate why the tree stops so short. Well, remember, it's really small data set. So one of the first things that affects that is the criteria, the tree. And it turns out the default criteria is actually based on not the percentage cases, but the number of cases. And other tools, other implementations of this algorithm are actually based on the percentage of cases. This is minimum number of cases. It says you can't have a parent node with a value of less than 100 cases. You can't have a child node with fewer than 50 cases. So let's just show you what I mean by that. That is a parent node, that is a child node, that is a parent node, and that is a child node. So it's just basically saying the group higher up in the hierarchy and the group lower down in the hierarchy, that's got to have at least 100 cases. That's got to have at least 50 cases. That's basically what it's saying. So we can change that because we've only got 300 cases here, and we can say we've only got 300 records. So we can go here and go to criteria and say, well, look, let's be a bit less harsh. Let's make it 50 and 25. So it means you can get group sizes of 25. Click continue at that point. The other thing that stops it from growing is, of course, is that it might not find groups where it might not find interactions where it's actually statistically significant. So we look at criteria here. We have shade here. It's actually the significance level it's looking for is a p-value of 0.05. It's using Pearson's chi-square. You could argue you should use likelihood ratio. I've never found it better. That's a bit stricter. And you could also make that 0.01. Again, you're being a bit stricter. It doesn't generally make much of a difference. You can increase the number of iterations. That's for the estimation of the probability values, but it's not terribly interesting. If you have any continuous variables in here, you can see that it's setting them to deciles of 10. And it says I can see 4 continuous variables. Those are denoted by the rulers. Those are set up, of course, if in the data set itself you have to tell it, if you haven't already done so, that they are scale variables or continuous variables. And you can change it from deciles to vintiles. You could say, actually, I'm going to make that, a group of 20. Let it break it into 20ths. Again, I haven't found it ever makes much of a difference, really, but you feel free to experiment with it. Certainly changing the growth limits, 50 and 25, that tends to create more detailed, larger trees. So let's click at that again, run that again, running the shade algorithm again. Okay, now it's created a more detailed tree. I'm going to double click on it to open it up. And I'm going to zoom in. So this is something I get into the habit of doing. I'm going to make that 150, 150%. And I'll go to options, ranges as text. And now we can see the same split as before, 0, 1, and more than 1. But this time it's more detailed. So it's saying if you've got 0 kids, 128 cases here. If you're not married, then 68% of people actually have the product. And if you are married, 19% have the product, which is interesting. And saying if you've got a mortgage, then 40% have the product. So that starts to increase a bit. If you don't have a mortgage and you're currently married and you've got 0 kids, then only 10% have the product, or they have the product from that bank at least. Whereas if they've got 1 child, then its age is the variable that splits it. And it says, well, you've got 1 child and you're age 41 or less, then 70% have the product. But if you've got more than one, if you're age 41 or more, and you've got 1 child, then all 32 cases in there, 100% in node 7, terminal group node, they have a probability value of 1. They have 100% of them have the product. And if you've got more than 1 kid, and it's saying, well, your disposable income, we've actually got income and disposable income. Disposable income is based on dividing income by the number of children, taking into consideration it's some sort of ratio like that. It's not exactly by the number of children, because obviously if you're dividing by 0, you're going to get 0, and if you're dividing by 1, you're going to get the same number. But it takes into consideration the number of kids they have, and obviously the more kids you have, your income is divided by that. And it's saying, okay, I find this threshold value here, $14,724.5, and it's saying if you're in that group, if you're less than that, 6.6%, only 6.6% have the product. So there's this weird interaction between the number of kids you have and your disposable income. Whereas if you've got a lot of if you've got more than 1 kid and you've got reasonably a lot of income, more than $14,724, then that jumps massively to 91%. So, you know, what's driving this, certainly for those with more kids, is the amount of income they have on the basis of whether or not they buy this product. And I could even go further and say, look, let's just go mad. And I'm starting to really get into very small group sizes here, but I could say, okay, I'll make that 20 and 10. So you can go down to group sizes of 10. I mean, you're going to be, if you be careful here, you can get statistically significant differences with group sizes of 10, but you are kind of, you know, flying by the seat of your pants somewhat, because you're starting to make generalizations based on, you know, only 10 records. But click OK. Let's see if it makes a difference. I'm just glancing up here. Mortgage customer. I don't think it's. No, I think we've kind of hit the same tree again. So it can't find any more significant interactions at that point. Oh, the only thing's different. Oh, I see. We've added an extra split here under the no group for mortgage customer. You can see under this no group here, 44 cases. We don't have mortgage customer, but whereas down here, it does split it. So it does give it a slightly different tree. And we can see that for those who have no kids, who are not married, and who have a mortgage, it's 20% of them have the product. And if they don't have the mortgage, then 93% of them have the product. So it's quite a big difference here. There are 29 and only 15 cases in these. So again, treat it with a pinch of salt. It's interesting. If you, and I've done experiments of this, when you have, if you take a very large data set and you say, okay, I'm going to take like a tiny percentage random sample of it and build a decision tree, as you resample that, the decision tree is quite different from one sample to the next. As you start to increase the sample size, you start to see the decision tree changes less and less. You know, if you take a random sample of, 10%, it's going to change a lot. If you take a random sample of 40%, it changes less. If you take a random sample of 80%, it changes less. So the tree becomes much more stable the bigger the sample size that you have, and of course, the larger the sample size in the subgroup. So it's something to bear in mind here, that it's like any statistic. It is affected by sample size. That doesn't mean that the statistical tests aren't valid. In fact, what decision trees do is they adjust for the number of statistical tests. So you can see that this one here is 0.001. That's probably, and this one's 0.002. So that's still less than 1%. Still less than 1% value in the probability value. And you can see here the accuracy rate is 91% and 82%. I would suggest that that's probably what we call overfitting the model. I think that would, if I were to test this against another 300 cases, I reckon that would not be 87%. I think this model is overfitted. I think it's found some quite esoteric differences in the sample sizes, where we've got group sizes here of 3 and 6. And I suspect it wouldn't be as accurate. You can actually test this if you've got enough data set. sample size by clicking on validation here. So you can do validation, and you could split the sample into 50-50 here. Say 50-50, click continue, and then see if you get the same tree each time. Well, let's see the accuracy down here. So this is 86% accurate, 77% accurate. It's better than I thought it would be, actually. You know, it's a reasonably big drop, as you'd expect about a 10% drop. It's better than I thought it would be. So it's saying that, you know, on the test group where we've held back, this is the test sample. This is what it looks like when we apply the decision tree based on only 152 cases here, roughly 50%, then applied to 148 cases. And you can compare and contrast that. I'm not going to get into the detail of that because we've got running out of time somewhat, but you know, this is how we would validate the tree if we're in kind of prediction mode as opposed to insight mode. And I do tend to see those as different things. Sometimes you're building decision trees to understand the drivers behind something, to understand what affects something, to understand the exceptions to the rule, to the interactions. Very insightful. But if you're literally trying to build a predictive model of a decision tree, then validation starts to get important. You also have cross-validation, where it folds the data into tenths and then uses randomly 90% of the data to predict the remaining 10% systematically as it goes through each fold in the data. Okay, let's go back to the criteria. I'm going to change this criteria back to 50 and 25, so we've got something a bit more stable. But now I'm going to compare and contrast a different method here, just so you're aware. CHAID is a method, but it's not completely what's the phrase? It doesn't go through every possible permutation when it comes to merging and splitting the data. For that, we need to have exhaustive CHAID. Exhaustive CHAID goes a bit further with regard to finding these splits here. So you can see here when I use exhaustive CHAID, I'm actually surprised it's done anything, because I usually find that the difference between exhaustive CHAID and CHAID is so tiny that it never makes it really doesn't change the outcome very much. But you can see here on the original tree, it split children into three groups, and it stopped at that point. It kind of stopped at that point. The algorithm stopped and said, okay, I can still maintain, you know, the overall significance level here of much less than 0.01 just by grouping together the 2s and the 3s. So 2s and 3s get grouped together. I'm quite happy with that. With exhaustive CHAID, we're saying go further. It's more resource intensive, but with a really small sample size of 300 cases, it really makes no difference. You're not losing anything by asking for exhaustive CHAID. I would say that you're not necessarily gaining much, generally speaking, but it is somewhat more intensive. So we can double click on it. Let me double click on it and have a look at it in more detail here. Let's go into, once again, ask for 150%, zoom into it. And it's saying, look, okay, let's go for options, ranges as text. It's saying 0 or less, 35.9%. One kid, 85% have the product. 1 through 2 means just basically higher than 1 through 2, means basically 2 kids, 38% of the product. And if you got more than 2 kids, 20% of the product. So it's just finding this little bit of extra nuance in the side here. It's finding these 35 cases where 7 of them had the product, and these people have 3 children effectively. They're in the 3 or 3+ group. That's exhaustive CHAID. CHAID is based on chi-square. It's a statistical algorithm. There is another algorithm called CART. Sometimes I don't think SPSS has the rights to call it CART, but it's called CRT here. It stands for Classification and Regression Tree. It uses a machine learning measure. It uses something called purity or a Gini coefficient. Click that. So it's a different method, but it's trying to do the same thing. It's worth trying. CART doesn't create these multi-branch splits. It splits everything into 2s. So it only splits everything into pairs. So if you wanted to split the over 13,000s again, it would just split them down here into over 13,000, and it would go 13,000 to 15,000, 15,000 and so forth and higher than that. Here it's creating a much simpler tree. It's saying, you know, I'm taking disposable income as my biggest split here, never mind, not children. It's a different method. It's using an improvement statistic here. This is a wee bit more obscure. We haven't got time to go into it, but it's basically a Gini value. It's a purity measure. There are other types of trees. There are at least other decision trees I know of are C5, which is another tree. It's C4 is another tree, and there's one here called Quest. There's lots of different decision tree algorithms out there. Shade was invented, I think, in the 1980s by Gordon Cass. CART was invented in round about the same time, maybe late 70s, early 80s, by Jerry Friedman. And these were pioneers in the statistical and machine learning field. So here it's saying, look, you've got less than 13,000, then 17% of them are in the yes group. If it's more than 13,000, 59% in the yes group. Number of children. Here, annoyingly, it says less than or equal to 0.5. I know that's impossible. You got 0.5 children, but it kind of treats everything as a real number as opposed to an integer. Let me see if I try ranges as text. Yeah, 0.5 or less. That just basically means 0. It's just annoying. It just means 0, and higher than 0, basically. Obviously, higher than 0.5 is 0.5 is 90%. And then currently married, it actually uses currently married, whether or not you're married. If you've got 0 kids, but your income is greater than 13,000, then 68% fall into that group. Let's see how accurate that is. 87, 75%. So it's an alternative approach, but quite accurate nonetheless. Okay. So let's just look at what else we can do here. Let's switch. There's another method here called Quest. I'm not going to touch that. I really don't recommend it. I don't think it's a very good method. I tend to use either Shade, maybe exhaustive Shade. You can use that. There's not much to split them. Or CART if I'm trying to build a predictive model and I'm looking at the accuracy and doing validation to check it as I'm going along. Let's go back to the Shade method here that we had earlier on and see what else we can produce from here. Well, if we look at the output here, we have decision tree. This is how you can have the tree in table format. You can actually have it add these values here, cost, probability, score values. What's that referring to? Well, you'll notice it says categories up here. If you click on categories, you can actually say, look, this is the category I'm really interested in, CS group. You say, that's the group I'm really interested in. And it's a way of pointing out that within your target variable, there is a target category that you're interested in. And that affects the output somewhat. It shows you, it gives you some extra details. It says, okay, if you're interested in this yes group, I'm going to take that into consideration. You've also got this thing called influence variable. That's a weighting field. So you might say that you might have another field in here. If you're familiar with weighting in SPSS, a field that doubles the representation or increases the representation artificially of different records. So that's just a weighting field. And force first variable is a way to get it to control, to actually say, look, I've got a key variable in here. I want that one to be the first one that goes in there, irrespective of whether it's not the most significant or not. So there I've added that. And if I go to output now, I can go to, let's see, statistics, cost, probability, score, profit values, and go to plots here. I can create things called gain charts, which are a way of representing the accuracy of the model, of predictive models. Gain charts show you how many of that shows you how many of the groups you would find, of your target group you would find. What else can I do? I can have the classification rules shown to me. I'll just run this anyway, so you can get an idea of it. Click continue and OK. Got the same tree as before. Now I'm getting gain nodes. What's that table here? It's saying that, look, if you wanted to find, your best node for your, now that we've told it what our target group is, it says it's node number 7. And node number 7 is this group here because it's 100%. Remember, that's the one where 100% of the people in the yes group. So it says basically that's your best node. It represents 10% of data. And it captures, the gain here, it says it captures 32 people of the 300 who bought that product. So you're gaining 23% of your target audience, if you like, your target group, the people who bought that product. And the response rate for it is 100%, which is, so 100% in the front, which is 222% better than the default, because the default is 45%. So it's saying, if you're saying, how much better is that than the baseline rate of 45%? Well, it's 222% better on it. And it says the next group is node number 9. So it's actually listing the nodes in order, saying what the best group. So node number 9 is, we can count across 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 91%. And again, that's 11% of the cases in that data. That's 23% of the respondents. So right away, we've got nearly 50% of the respondents. We've got like 46.7% of the respondents of the people who bought the product in 2 nodes. We've captured them in 2 nodes. And that there one there represents 202% index. And the S group here was shown as a gain. This is just basically saying that these gain charts here, which you get a lot in predictive modeling. So, I spend a lot of time doing predictive modeling and assessing whether or not a predictive model A is better than predictive model B. And I'm using charts like this and ROC curves and so forth to do that, lots of different curves. But it's just basically saying, look, if I only had budget to say target 35% of this audience here, I can't send an offer out to everybody that predicts to be a yes. But if I pick my best 35%, my nodes, if you like, my best nodes that find 35% of the data, of my best 35% of the data, how many of the yes group, how many of these people who buy this product would I find? What would be my hit rate? And it says, well, if I read that off, it says we'll come in probably about 65%, 68%, something like that. So it's telling you how many you would gain. And that's what it's used for. It's helping you to figure out how many you have to target in order to hit your, the requisite numbers of percentage. And then the accuracy is at the bottom here. And then it shows me the syntax it would produce for that. So it actually shows me the syntax it would produce for that if it wanted to run it. And in the same sense, if I run this again, I'm going to go back to output here. I'm going to switch some of the stuff off and say, okay, look, I'm not really interested in these other values here, like plots. I don't want the gain on. I don't want the rules on. Don't show me the classification rules. But I can ask for things like I can ask for this stuff. I can ask for like a variable importance plot. Show me the important variable is. I'm running out of time here, so I'm going to hit save. I'm going to show you that you can actually save out the selected variables. Actually show the terminal node, the predicted value, and predicted probabilities. Click continue here and click OK. So this is when we apply the model back onto itself. We say this guy here belongs to node number 7. That model predicts them to be in group 2. And the probability of them being a respondent, of being somebody who buys home insurance is 100%. It's 1. So they belong to that special group of node number 7. Here it's only 7% chance. Here's a 10% chance. Here's a 91% chance, and a 68% chance, depending on which node they belong to. And there's only a limited number of terminal nodes. If I click on this, you can see that it's actually, these are the terminal nodes that's listed here. That's not a vast number. So that means you're only getting 1, 2, 3, 4, 5, 6, 7. You're only getting 7 different probability values out of this tree. But what I could do is I could take this decision tree and I could save it. I could click save here and say, okay, I want you to actually save it away as a little file, and I'll call it insurance. I think it's home insurance. I hit save, and it saves it as a little file. It calls it an XML file. Click OK. And then I could open up a new data set and say, okay, look, these people here haven't got insurance. I'm going to call it insurance scoring. Don't want to save that. Got insurance, that they've got everything else, but they haven't got insurance. And I want to apply that model to it. So I go to utilities here. I go to scoring wizard. And this is where we can apply a predictive model, any predictive model, not this decision tree, but any predictive model we produce in SPSS. To a current data set. I'm going to say, okay, there you go. This is this insurance model here. It says I'm looking for these fields in case they're called something else. Maybe it's called disposable income or something like that. You can actually map it to the correct field. Hit next here. And say I want the predicted value, I want the node number, I want the confidence, and I want the probability of the selected category, which is I think category 2 to be a yes. I can't remember, but it doesn't matter. You get the idea. You could look that up. Hit finish at that point, and it shows me, what node they belong to, whether or not I think they're a category 2 or not, and what the probability is of them being in category 2, which is I think is the yes group as opposed to 10 group. And then of course I could I could sort that in ascending order if I wanted and say, okay, or sort in descending order. Say, right, I'm only going to pick people, who are above, a 50% chance or something like that. So everybody here, and say I'm going to slice everybody's got greater than 50% chance of being in the yes group, and I'm going to target them. And that's how we port or apply the model. Finally, I just want to show you very quickly here, because we don't have to just use this type of operational type data here. We can use a different data set. I'm just clicking open here, open data. Here's one which is HR survey. Let's go to output. I'm going to close down the output, so just get rid of it. We'll do the same thing again. This time our decision tree, we're not really trying to predict, whether or not somebody has whether or not somebody is going to buy a product. We're going to see whether or not an employee leaves within 1 year, 2 years, or 3, or remains at least 5 years. So this is a HR survey, and we can click OK at that point. And you can see it's a different type of tree, because this time it's very shallow because I've restricted it, of course. But this time I can zoom in at 150%, and I can ask it to show both leave within 2 years is the blue group, stay 2 to 5 years, leave after 2 to 5 years is the red group, and remain at least 5 years is our orange group. And we can see what affects that. And we can say, again, go to options here, ranges as text, and we say, if they say attitude of senior staff is fair or less, then 82% say they're going to leave within 2 years. So that's the single biggest discriminator between those who remain and those who stay. And this is a 3-category outcome. Whereas if they say it's better than fair, but it's up to good, then the majority group is leave 2 to 5 years. And if they say it's better than good, higher than good, then 74% say to remain at least 5 years. And then we can go into each subgroup of that and say, well, what else affects it? General environment, working hours, holiday entitlement, social events organized. And if it's too complicated, you can actually just show it as a series of charts, almost like you're filtering sand, trying to find the orange group, people who remain at least 5 years, and compare and contrast that with the blue group, those who leave within 2 years. So another, it doesn't have to be a binary operational outcome. It could be a attitudinal outcome of that type. Okay, just in the last minute or so taking you through that, remember that we can also use decision trees for drivers of satisfaction. We can use it for demographic profiling. So if this is a particular group or a particular demography, and we're saying, well, who belongs to that demography? We can click on that. We can use it to interpret clusters. For example, if you're doing a cluster analysis, it's going to produce clusters 1, 2, 3, 4 for you, or something like that. And it's hard sometimes to differentiate between one cluster and another cluster. Here we can see, for example, that cluster group 4 are people who bought beer and who bought canned vegetables, whereas down here, cluster group 3 are people who didn't buy beer, but they definitely bought wine, and they didn't buy canned vegetables. So you can see people in that group. Bear in mind, we have a number of training materials which are free to Smart Vision customers or are available for purchase from non-Smart Vision customers. We have training courses to go into this more detail. And bear in mind that we offer a lot of consultancy services, whether it be 1 to 2 days, or 3 to 5 days, or something deeper that's what's worth minding. And that you can source your software directly from us, particularly your SPSS software. We can assist with help with piloting, implementation, and support of analytical tools. We offer formal classroom training or virtual training, custom course development, or even informal bite-sized training split over time. We offer no strings attached technical business advice to customers and non-Smart Vision customers. You just need to give us a call. And we also have formal track technical support services around the IBM SPSS product line. I do hope you find that useful. In our next session, we're going to be looking at Bayesian statistics in SPSS. And then in the last session, we're going to be looking once again at predictive modeling, but we're going to be using data robot to do that. So we're looking at data robot and predictive modeling. Thanks very much, and we look forward to logging in again in the near future.